Hello there, ladies and gentlemen, boys and girls. Today, this video here is to show you two of the types of wave behaviors. Where today we're going to be talking about absorption and something called diffraction. All right, so let's get at it. Let's make sure we have our handy dandy notebooks out. All right, so first of all, a wave behavior. All right, this is what happens when a wave approaches a new medium. All right, so I'm talking sound waves right now. Those sound waves are hitting all different kinds of surfaces. They're hitting the wall, they're hitting the floor, they're hitting the ceiling, they're hitting my computer screen, right? They're hitting the speaker, or excuse me, the microphone. And now it's going to do one of many things. All right, it can be reflected, it can be refracted, it can be absorbed, or it can be diffracted. All right, and so we're going to talk about diffraction and absorption today. All right, so let's talk about absorption. Just thinking about it real quickly, this one should be a pretty easy one because we talked a little bit about this when we talked about colors, and we talk about when we talk about what we see, all right, why we see certain colors, and we also think about we have some experience with something being absorbed, right? Whether it's light and waves or water being absorbed by a paper towel, right? That paper towel then takes in the water, right? And that's a good paper towel is going to have good absorbance. All right. The same thing is happening with a light wave. But when a light wave hits a new medium, all right, at times that wave, not always, but a lot of times that wave is then taken in. Now remember, a wave carries energy, so when an object absorbs wave energy, then it's taking in that energy as well. So if that's thermal energy, then that warmer object is going to warm up. All right. Just depends on what kind of energy it is. If it absorbs kinetic energy, all right, if something hits me and I'm going to absorb that kinetic energy. All right. So we talked a little bit about this when we talked about different colors. So let's say I have three colors here. I have a red wavelength of light, green, all right, and blue. All right, all three of those colors are going to hit this block. Now, we talked about the other day, the reason why we see the things that we see is because of what hits us in the eye. So if light waves were going to hit this block here, the green wavelength is going to reflect and thus go to our eye and we see it, while both red and blue are absorbed. So it takes in that energy. All right. If I have a color or an object that's going to appear the color black, so when I have that red wavelength again, a green wavelength of light, all dependent on different frequencies and wavelengths. All right. If that object appears the color black, or at least what we call the color black, that means that all of those wavelengths, all three of them, are going to be absorbed. All right. All the colors are absorbed. All right. Now, finally, if we have or something that is a white or white block, we have red, green, blue. In this case here, black is the absorption of all colors. White is kind of its opposite. For me to see the color white, my eye has to absorb or has to absorb all of the light waves. So blue would reflect. Green would reflect. And red would reflect. None of the colors are absorbed, and so our brain, since it's getting all the colors that reflect off of it, processes that as the color white. Oops. So in this case here, there's no absorption. Every material has lots of different variables on whether not just its color, but its texture and its material, what it's made out of, have different levels of absorption. Color is just one of the easiest one. It's one of the reasons why we like to wear light colors during the summer. It reflects more of that light. If I wear very dark colors, a dark black hoodie during the summer, I'm going to feel very, very warm because all those light waves are going to be absorbed from the sun into that hoodie. And I'm basically just going to be wearing a warmed up hoodie at that point, which is not always fun to do during the summer. All right. All right. So that's absorption. All right, absorption is a pretty straightforward one. Diffraction is one that we don't experience necessarily every day, or we're not used to seeing. All right, it's not one that they necessarily talk about in like elementary and middle school. All right, and this one is I'm going to use an example of sound waves here, but a lot of times when this actually was first discovered, it was discovered in light waves. And I'll show an example. I'll show an animation example of this in a second. All right, so what we have is diffraction here. So if I were to feel very, very frustrated at the end of a day, all right, and I just start screaming, and I'm sending out sound waves in every direction, it's going to approach this new barrier. But now when this new barrier has like a small hole in it, or I say a slit for those waves to go through, something very unique is going to happen. All right, these waves right here at the edge where it's hitting the boundaries, they're just going to reflect off, right? This waves here is going to reflect off and reflect off here. That's not diffraction. Diffraction is when it goes through, or is when a wave goes through a small slit. All right. And what's going to happen is it's when it goes through it, once it goes through that boundary, it's going to start to kind of wrap around it. All right. So someone who was maybe standing right here, even though they can't see me, but they can hear me. All right, because those sound waves are going to diffract around a boundary, or what we would say is absorption is taking in, because I want to just simplify it. Diffraction is moving around. Not just moving around anywhere, but like around the border, around the boundary. All right, in this case here, if it hits like what we call a slit, then it's basically going to bend around it. All right. So let me show you a quick example of this right here. Okay, what I have here is a simulation that is showing these waves here. So we see here, this is a wave generator. The little like stripes indicate like crests and troughs, so we can see measure wavelength to wavelength. All right, and when you see here, when it's hitting this boundary, right? So when it's hitting this boundary, the waves are either going to bounce off, be absorbed, all right? But if they don't go through it, when they go around a boundary, you're going to see how it kind of fans out. All right, this is what we call diffraction. It doesn't just come across as like a straight beam. See how over here, there's waves over here and waves over here. This is what indicating what we call diffraction. Again, this was actually first discovered when using light waves and not actually sound waves. So when they did this experiment with light waves, physicists, they found out when you shoot light here through a very small hole, what you would end up seeing is something like this on the other side. And the reason for that is because that light wave, as it goes through that very small hole, is then going to fan out and diffract around that, or on the other side of the hole, and you end up seeing these concentric screens. All right, so that's it for diffraction and diffusion. Diffraction and absorption, sorry. If you have any questions, don't hesitate to go back and watch the video. These are two of the wave behaviors, what happens when a wave hits a boundary. It's either going to be taken in and absorbed or move around it, which we call diffraction. All right, thank you very much for watching. Like I said, if you missed anything, just go back to the video, pause it. Otherwise, good luck, and may the science be with you.